Okay, so here's the last example that wasn't covered last day. Essentially, the idea is I'm going to give you some data, and we're going to use it to try to make a educated prediction about what's going to happen. I mean, look at this data here. There were only 16 bears in the park. That's not a whole lot, right? Hopefully, the bear population can grow over time, because eventually we get to the point where there's 18, 21, 26, 33. Now, but look at the rate of growth. From this year to this year, it went up by 2, right? From 2007 to 2008, it went up by 3. Then it went up by 5. Then up by 7. Then up by 5. Then up by 7. Then up by 9. Then up by 9. Is that a consistent rate of growth? If it was consistent, what kind of function would it be? If you had consistent slope. Good job, guys. Yeah, since this clearly does not have a consistent rate of growth, it's not linear, it sure looks like it's starting to be more of an exponential function. So one of the things that your calculator has the ability to do is it's called regression. Okay. Grab your calculators here. I'll walk you through the buttons on this again. This is actually one of the most useful things that you might actually like. Most of what we do in math, little secret here, everyday life math. You're not going to use this in life. This one thing right here is something that could be used. Press edit, and it gives you an L1 and an L2. L1 and L2, by the way, stand for list 1 and list 2. Basically, you're going to list some data. When you guys are in my physics class, think of it like your table of values, right? This is essentially a table of values. Easy enough. Once you have it, you press stats. You did some stats, or around your calculator has the ability to create regressions, and they all end with reg. What a regression basically is this will make sense for the class. You know how like I give you some data, and in physics it's always in a straight line. I've always given you straight line data, right? And then I ask you to make like a line of best fit that goes through the data, usually so you can find your slope. Well, that's you were doing regression. Right? Regression is basically put a line through your data. Now, it's a lot easier if it's linear because you literally just take a ruler and just draw a ruler through it, right? But what if it's not linear data? What if it's quadratic or cubic or whatnot? Well, your calculator basically has a way of calculating that for you. This is pretty intuitive. Come on, board. You worked yesterday. Can you guys see? I can't change this while I'm flipping the battery out. But can you see how it goes like lin reg, quad reg, cube reg? I mean, hopefully that makes sense. Essentially, the idea is that if you had data that was linear, you'd use this one. If you had data that was quadratic, you'd use this one, right? So it basically what it does is it makes a line of best fit through your data points. So if you were to kind of scroll down, if you get down to 0, it's exponential regression. If you have data that seems to be of an exponentially growing kind, then all you have to do is know how your function works in your calculator. And everyone's is a little different. A few of you, I showed you, it literally will tell you that L1 and L2, like it pops up right away. If it doesn't do that, you have to tell it where your data was. The reason why you need to do that is that maybe your data wasn't in list 1, list 2, maybe it's in list 7 and list 8. So to find those lists, it's second L1. And then if you're doing it this way here, you have to put in the comma, just because it separates like parameters in your function. Then your other data was second L2, comma. And then this is the one where everybody needs to join back together. You have to tell it where to put your graph when you're done. You basically want a y variable. And for those of you who have like the other type of screen on your calculator, you're looking for store reg eq. You guys see where it says that? Store, where to store your regression equation. Basically, it's asking you, where do you want to put it when you're done? I can make you an equation, but we need a location for it, right? So we want to store it in your y equals. Like, we'd sure love to have it show up right here. So essentially, you have to find the y variables. So this is the button combination. You have to press the variables over to find a y variable, y variables. We're working with functions. And then literally just pick any of these y values. I could care less which one you pick. So like if I were to pick, for example, y6, and I put the y6 right there. Now I'm going to press enter. For you, those of you who have the other calculator type, you have to go down and press like maybe execute calculator. Okay. Right, so I'll press enter. And it'll do two things. One, it'll actually tell you an equation in the form a times b to the x. It does that because this helps me re-illustrate with you guys the terminology we have. This a value right here is your leading coefficient. This b value right here is your base. And if you go to y equals, in y6, there's an equation for you now. Does that make sense? So let's try this question now. I need to now plug in this data right here. So if I'm going to do that, I go to my calculator, I go to stat, and I go to edit, and I have to start typing in some of this data. We should, yeah. I mean, no different than like if you guys were doing a graph in my chem or physics class, you should graph all of it because we want to make sure that the line is a line of best fit through all of these points. If you skip a point, it doesn't fit as well, right? So like in the L1 column, I'm going to go 2006, 2007, and so on. And then in the L2 column, I'm going to go back and do the number of bears, which was 16, 18, and so on. So essentially, you're making a table of values. If that makes sense. I'm probably going to have you guys do this in my physics class at one point, actually. Because this is actually quite a useful tool to basically be able to create yourself an equation. 2007, 2008. Try to get as far as you can and then go do the exact same steps I described for you where you type in exponential progression L1, L2, Y, something. Let me know if you don't get to the point where it says overflow, but I want to describe for you why it says overflow in a second. Also, whenever your calculator gets to the point of overflow, it's because it has it's got such large numbers that your calculator can't handle it anymore. Essentially, your calculator can handle numbers that go up to E99. Like if I give you one E5, you guys know E5 is 5 afterwards, right? Your calculator only handle numbers up to the value of E99. And then as soon as you have 100 zeros afterwards, your calculator has to be quick. That's how it's programmed. And so what ended up happening here is because we were using the years 2006, 7, 8, 9, and 10, your calculator was really struggling with that because of the fact that it wants to regress it back to year 0. Right? What we actually were doing was finding what happened 2,000 years after our initial date, which would be like year 0 when they changed from like the count from BC to AD. You guys know what I mean like that? Because we were going so far in the future, some of the values were too large for your calculator to handle. Or the other way of approaching it is actually trying to calculate values so small, because the first thing your calculator want to do is figure out what happened in year 0. How many bears were there in year 0? Well, if you kind of work this backwards and go, well, it used to be or 16, right? When in year 0, they essentially 0. Probably what happened is your calculator tried to make it like 0.000000000000000, something along those lines. And it probably gave up, saying, I can't handle more than 99 zeros in front of the number. Okay, so I got to show you a trick here to fix this. So that's my starting year. And then call it year 2, year 3, 4, 5, 6, 7, 8. And that's a useful trick because it shouldn't really change the way your calculator graphs it. It's just rather than trying to do it 2,000 years in the future, We just are basically saying year 2006 is actually year 0. Did that logic make sense to you guys? Emily, I'll have to look at your calculator and figure out why yours was able to regress. So 0, 1, 2, 3, 4, 5, 6, 7, 8. But so now if you do it and go stat, calculate exponential regression, did it give you an equation this time? L1, L2, Y, I don't know, Y1. Okay, did you guys get this equation here? Check your equation. See that it gave you 15.39 and 1.16. Can I talk about that? Okay. The A value is your leading coefficient. It's from the years. Adding years 0. We just find. You guys good? Okay, we just find year 0 as 2016. Now I know that on the screen there it says 15.39, and on the table it says 16. The reason why, keep in mind, this is a line of it's related to the point there. It's connected dots. It actually makes it like as close as it possibly can to a smooth curve. But would you agree that 16 on the one table and 15.39 is pretty close? Okay. What was the average rate of increase from year to year? Try that again. What was the average rate of increase from year to year? As a percentage. What percentage of growth was there? Are we all clear that this would have been a growing graph, right? This graph is clearly getting increased, right? Is it doubling? Is it tripling? Is it going up by 5%? Is it going up by 7%? That's what the B value is going to help us with. So by what percentage is it going up by? How did I pull the 19.6% out of there? Yes. Right, because if you multiply by 1, you have an exponential function, right? If you multiply by 1, you just keep what you have, right? But if you multiply by 1.9, you're keeping what you have, and you're going up by 19% more, right? Because really 0.19 is 19%. Right? If you're going up by 50%, it would be 1.5. Unless it's like such growth, like let's say you had 100% growth, it would actually be 2. What if you lost 5% every year? What would your number be then? If you lost 5%. Exactly at 0.95, right? Because 1 is not your standard stasis value where it's not moving, right? And you go up 1 and grow 1 like 0.9 would have decay. Fair enough? Okay, last step here then. Here's where this is useful. And this really dovetails nicely into today's topic. We now need to solve this function. So if I go to my window size and I make x go from 0 to 10, and I make my y value go from, let's say, 6, well, not 16. Let's do, well, yeah, let's go 16 to 64. And I were to graph this thing, hopefully I'd get a nice incrementally growing graph. Right? That looks like we're expecting. The question here is, though, when will we end up with 200 bears? Is 200 bears an input value or an output value? Is 200 bears an input value on this function or an output value? Is it x or y? It's y. So do you remember how to solve this? You'd like go over here. You'd throw on 200 as a new y value. Now, if I press graph, would I actually see another line on it? So I have to change my window. it's probably not 10 years later that we get to 200 bears. So maybe I'll make it like 20 years later, and I'll make this go up to 100 and no, 220 maybe. There, now my graph is growing. Here's a line straight across the top. If I intersected, what am I looking for if I intersect? The x or the y value? Because what's the y value going to be? Yeah, 200, right? So if I do a quick intersect thing here, the y value should be 200, meaning, yeah, we're going to have 200 bears. How many years later? Yeah, about 14 years. Can you guys see the practical applications for this? Right? This is one of the few times where I can tell you, look, I promise you, math is useful somewhere, somehow. Might not necessarily be your field. Dash 1 math is a lot less of the real world math. But this is a good example of how, if you now know what a function looks like, you can predict growth and figure out, well, this is when we expect something to happen. A good example of this, in a bad way, would have been China's one-child policy. You might have some relatives or know some experience with this. Can you That's solve that problem. Can you explain to everybody else what the one-child policy basically was? Their growth was continuing exponentially, right? And they realized that China as much as they would be able to afford to have 3 billion people in China. So they tried to artificially suppress the growth rate. We're actually going to problems now, I understand, though, because now that the oldest generation is like getting to their later. So it may have backfired to some degree. Um, growth rates, right? Because you can imagine people growing fruit flies was exponentially. We have darn things because they just kept growing, right? That exponential curve. Anyways, that makes sense. That's clear. Okay, cool. Because that dovetails nicely. We need to know how to solve these things. Remember how I told you that there were like there's 4 types of functions and 3 things you need to be able to do with them. Okay, the 4 functions are your square root graphs, your fraction graphs, your exponential graphs, and your log graphs. So we're like halfway through here, right? And the 3 things you need to know, part A, do you know like the subtle nuances of these things? You can't square root negatives. You can't divide by 0. Do you know what the graphs look like? Part 3, though, is you need to know how to solve. Well, that's what we just did. We just did a solving example where we tried to figure out what x was. Right? Now, one of the ways you can do that, if possible, is in your graphing calculator. Take one equation, which is going to grow. Take a second equation, whatever it looks like, and just find where they cross. Like, literally, that would work for you. And so to save some time here, can you guys fast forward in your notes here? I've got a slide right here which actually goes through some of the ways that we can solve. One of the methods is graphically. This is a picture of the question that was 2 slides ago. Like the question 2 slides ago, I'll flip back. You guys stay on the slide, okay? The old equation was x to the 3/8 minus 2, 3x minus 2, and 16 to the x plus 1. Hopefully you guys would agree that both of these are growth graphs, not just regular growth. Like these things are growing, right? Well, look at these 2 graphs right here. These are essentially 2 graphs that are just skyrocketing, right? I actually had to change the window size in the y value exceptionally high, but one way I solved it is literally just by finding where the 2 graphs crossed, and there's my answer, right? So that's one tool that I think you guys all have in your toolbox. My goal today is to show you how to solve them using something called like basis, and then Kelsey will show you how to use logarithms next week. Fair enough? So this is kind of the part C. So flip back here. Let me show you how we can solve these. Let me focus a bit on the terminology again. These guys all have a base of 8 and 16, right? You guys differentiate between a base and an exponent. What are the leading coefficients? 1 and 1. Good. So we really don't have leading coefficients to deal with right now. If we did, that would change things. But right now, we'll keep it simple. most of the first examples we'll give you don't have a leading coefficient, but keep in mind they could as we go forward. Fair enough? Okay, so let's talk about this base of 8 though. What if I wrote 8 as 2 to the 3? 8 is 2 to the 3. You guys have heard that at some point before, right? Well, if I rewrote 8 as 2 to the 3 and I put it in a bracket, I'd still have to have that 3x minus 2 kind of sitting there. But does that feel logical? 8 is 2 times 2 times 2. What about 16? Can I write 16 as some sort of further base exponent kind of scenario? Not 2 to the 3. You're close, though. 2 to the 4 would work. 2 to the 4 is what 16 is equal to. But it's still got to be multiplied by x plus 1. Yesterday, one of the things Kelsey did for a little while was she reviewed your rules of exponents. What we have here is a scenario where you have 2 to the 3, but you still have this 3x minus 2 right here. Here's what this becomes then. You guys see how I pulled that off? That's a 6 over there, by the way. That wasn't my best 6. How did I get from this step here to this step here? What did I do? Yeah, the rule for exponents here, if you have like a double bracketed double exponent kind of scenario, is you multiply, which for us means you FOIL. You guys able to follow this stuff up till here? Haven't lost anybody? Okay, now I want to talk basic rules of math. In math, you're allowed to do so many different math operations as long as you do it to both sides of the equation. For example, if I wanted to add 1 to both sides, this would still be valid. If I wanted to divide by 7 on both sides, this would still be valid. If I wanted to inverse sine both sides of these equations, that would still be valid. Well, now let's go backwards here. I'm going to go to my computer just so I can type the undo screen. That also means that I could undo an inverse sine from both sides of the equation. It means that I could undo a divide by 7 from both sides. It means it could undo a plus 1 from both sides, which means that I could essentially undo the bases that are on both sides. Follow that logic? Why would that not make sense, right? I can add 1 to both sides. I can subtract 5 from both sides. I could put a sign on both sides. I could put a base on both sides. I could make something, like for example, if I had 2 equaled 2 plus 2. No, that's not right. 2 times 2. There we go. I could add an exponent to both sides. So long as I do it consistently, that's still valid, right? But what's to stop me from then just removing a base? It's on both sides. But it has to be of the correct formatting. It has to be a single base to an exponent equals the exact same base again to an exponent. If you have a leading coefficient, it buggers the whole thing up. So one more time. You have to have base to an exponent equaling the same base to another exponent, no leading coefficients. You can cancel those bases. Well, at this point here, it's easy to solve. What you have left is 9x minus 6 equals 4x plus 9. Let's just kind of put that stuff off to the side here. Oh, that's a 4, isn't it? That's a 4. Sorry. I'm doing a very poor job of writing here. Subtract 4x from both sides. Add 6 to both sides. Let me know if I lose you. You get 5x equals 10. So x equals 2. So, sorry, it's a bit of a mess here. Let me walk you through the process here. If you don't have leading coefficients, that's requirement 1. You cannot have a leading coefficient. It buggers things up. It's a good math word. Buggers things up. Okay. If you can make it so that you give them the same base, mathematically, if you have the same thing on both sides of an equation, you can cancel it. So there's a couple of ifs. This is a very, very selective possibility, which is why we have to show you how to use the graphing calculator as well, and how to use logarithms as well, because there's actually alternate ways to deal with, like if you threw a, come on. This thing's not working quite as well as it was before. if you threw a 7 in front of this guy right here, you can't do that anymore. That screws it up. Okay, let me go to the slide here then. So you know how for the last year and a half of me teaching you math, I've always said wait for the opportune moment? I got another one for you. Okay, so when working with polynomials, the opportune moment really occurs when you can make it equal to 0 and you can factor. That's your like opportune moment. That's what you're aiming for. Right? Don't try to use the quadratic formula until it equals 0. Okay. When you have radical functions, your opportune moment is when you can square both sides when you have one of the square roots by itself. That's the right time. Rational functions, common denominators. You need to have fraction equals fraction. That's your right moment. So what we're going to focus on now is in exponential functions, you want like bases. If you can get to that spot, it's actually not that hard to solve. So let me do a bunch of examples now. So let's do this one here. First issue, do we have any leading coefficients? Good, because if we had leading coefficients, this isn't going to work. So this 27 right here and this 1 over 9, those don't currently have the same base, right? They're clearly different. But what if I played a couple of tricks on it? 27 is 3 to the 3. Let me know if I lose you on that logic there. 27 is 3 to the 3. But it still has to go to the power of the remaining x plus 3. Good on that one? What about 1 over 9? 3 to the negative 2. Good job. That's what you said, right? Yeah. Does that make sense to everybody? Why it's 3 to the negative 2? The negative because it's on the bottom of the fraction. And then 9 is 3 squared, right? So this is really 3 to the negative 2 to the power of 2x minus 5. I'm not quite ready to cancel yet. I'd really prefer it if you waited one more step and made this 3 to the 3x plus 9 and 3 to the minus 4x plus 10. I think that fits way better to do like the expanding first. And now you're at the right step. You have no leading coefficients. They both have the same base. It's on both sides. Cancel it. 3x plus 9 equals minus 4x plus 10. So what does that give you? 7x equals 1 over 7. There, x is 1 over 7. Able to follow that? So, one of the things I point out to Kelsey is I repeat things a lot, so I hope I'm not being too repetitive, but I think it's important. When is this method useful? It's very, very restrictive. Give me one of the conditions that has to be met for this to work. Can't be a leading coefficient. That screws it up. That's step one. The other requirement, you have to be able to get it to the same base. Yeah, if you cannot get it to the same base, this won't work either. Hence, graphing calculator. I mean, most of you guys, could you not type this in as y1, this in as y2, and just find where they cross? It's probably way the heck up there, but like you probably can find it, right? But this is the reason why we need to do logarithms as well. Like we need to have multiple tools. I like the analogy of a toolkit. The graphing calculator is like a hammer. It's very not subtle. It pretty much works, but if you want to bang away at something until it works, you can just do that, right? Whereas like this one right here is kind of like an in-between method. It'd be like using duct tape to fix something. Logarithms requires a lot more finesse. It would be like using like a skill saw or something like that. You know? So this is why you probably heard kids talk about logarithms with like, oh, they suck, because they're the most challenging of all these methods. You had a question? Well, if this base equals this base, shouldn't this exponent then equal this exponent? Like even from like a substitution point of view, doesn't that kind of make sense? Where like, you know, if this guy is the same as this guy, then shouldn't this one equal this one? So I mean, what you're basically are doing is an equation, and this equation is just of exponents. But does it really matter? You're still trying to solve for what x is. I get what you're saying here, right? It's a different way of thinking of it, because normally we don't just stop having them be exponents, but okay. Come on board. Oh, let's try another example. This one here. I put a little note on here. Don't forget to check your work. You can do that in two ways. Option one, type all of the equations in your graphing calculator, find where they cross. Option two, and this is actually the most brilliant one. Let's say it's a multiple choice question, and they give you four options: 3, 5, 7, and 9. Why don't you just take those four answers, plug them in for x, and see which answer makes both sides equal to each other? That actually is a real time saver. But if that's not an option, then you need to try some other methods. So, okay, what do 8, 16, and 32 all have in common? They all have a base of 2. So, I mean, good news. We can start with this whole base concept. 8 is 2 to the 3. 8 is 2 to the 3, but that'll still be to the x plus 6. 16 is 2 to the 4, but that'll be to the 2x minus 1. And 32 is 2 to the 5. But it's still got to go to the 3x minus 4. Common mistake. Kids will start hacking away at these 2's. Not the opportune moment. Because for this to work, we have to have one 2 with a exponent equaling another 2 with an exponent for that whole thing that Michael was kind of chatting with me about there, the idea of like, well, now the exponents are equal to each other. That's not really going to work when I've got, this thing isn't going to work. I'll just sit here. Range won't be an issue anymore. That's not going to work with that extra 2 on the bottom though. You guys get where I'm going here? Does anybody remember the rules for dividing exponents? Yeah, you subtract. So this is actually 2 to the 3. Let me undo that actually. Fix that. Well, okay, I'll just do that. This is 2 to the 3x plus 6 minus 4 to the 2x minus 1. You can actually write it as just one collective 2, because these two things right here, the rule for these guys is to subtract them. Do you remember that rule? Like essentially it looks like this. If you have x to the 7 over x to the 5, it's equal to x to the 2. X to the 7 divided by x to the 5 is x to the 2. Why? Well, you have 7 x's on top and 5 on the bottom, so 5 of them cancel out and there's 2 left. Those same rules still apply here, but it's just a little bit different. You have 2 to some random gobbledygook. You have 2 to some other random stuff, right? We'll just take your 2 random stuffs and subtract them. Very technical words. Kind of like not ins. You guys able to follow that so far? 32 is 2 to the 5. This 32 right here is 2 to the 5. But now I can cancel my 2's, and now I just basically have a line of linear algebra to work with. So let me know if I lose you. You've got 3x plus 18 minus 8x plus 4. Don't forget that double negative. The minus 4 times by the minus 1 is a double negative. And then you have 15x minus 20. If it's okay with you guys, I'm just going to stop here. You guys know how to solve from this point, right? Combine your like terms, solve for x. I want to save some time. I'm going a little longer than I wanted to today. How am I doing? Able to follow this? Sweet. Okay, so quick recap. If there's no leading coefficients, parameter 1. If you can write them all as like bases, parameter 2. You have to make it so that you have a single base to an exponent equals another single base to an exponent. If you don't have that, you have to do some work to get there, right? Hence the whole, there were 2 2's here. You can't just hack these guys off like that and just say I'm good to go. That's not how it's going to work. So we had to do a little subtracting rule on this guy right here. Once I get there, then it's just linear algebra. Then you can just solve for x. So the last thing I kind of want to weave this into then is, I think I kind of been lying, I guess. You know how I've said there's like been 3 things you need to be able to do? There's actually a 4th, but this 4th one permeates throughout the entire course. In pretty much every type of function I have to teach you, from polynomials to non-polynomials through to our next unit on trigonometry stuff, you're going to get word problems. Okay? And kids usually hate the word problems because the big difference is that rather than me giving you an equation, you have to write yourself your own equation and then solve it. Right? Like if I give you an equation and say, here's an equation, solve it. Most kids are like, I can do that. But if I give you a word scenario and say, here's a scenario, write yourself an equation and then solve it. Most kids, they get frustrated because step one is to write yourself an equation. And if you can't write yourself an equation, how can you solve it? You know what I'm saying? So I don't have like some magic bullet where it's like, here, just do this. It solves the problem. The best advice I have for you is lots of practice. The more practice you get, the better you get at writing your own equations. So anyways, let's try some. You got a bacteria that starts with 3,000 bacteria. Stop. What is that, 3,000? Yeah, I mean, if I write myself kind of an equation, it means that we're starting with 3,000. Right. After 3 hours, the estimated count is 48,000. Okay, maybe I just have to tell you the first one here. The 48,000 is a fancy way of me telling you that this is your y value. At some point, you're going to have a y value of 48,000, and the time it's going to take is kind of your x value. So in a way, I'm kind of giving you the x-y coordinate pair. So the y number kind of makes sense to just go over here, right? Because that's normally where you'd write it. It's like y equals a leading coefficient times by a base to the power of an exponent, right? So it means that my x value is 3, kind of up there in the corner. But I'm missing a few things. What's my base? What's my base? What's happening to our bacteria? They are eventually going to need to double. So my base needs to be 2. So quick recap. You start with 3,000 bacteria. It's going to need to double. We know that it doubles at the coordinate point 3, 48,000. This is where kids, they struggle on this the most. It ends up being like 3 over x. The reason why it's 3 over x is that the top part of this fraction is the running counter time. Like this is how long it's actually been. It has been 3 hours. The bottom of this little fraction right here is like the period. I think she used the word period yesterday. It's like how long will it take for it to double? We don't know how long it will take for it to double. So it's actually the bottom of the fraction that's x. Does that setup make sense? Okay, well, now let's solve. Now, one option, you literally could type this in your graphing calculator, find where they cross, and ta-da, you're done. That is option 1. But I feel like most people, if you like my analogy of tools, are pretty good with a hammer. That's not a challenge. So let's work on option 2 using, I don't know, duct tape. It's not nearly as challenging as the logarithm method, but it does require a little more work. However, everything I've been telling you for the last 20 minutes, there's actually parameter 1 isn't being met right now. Parameter 1 is no leading coefficients. But that leading coefficient there, right? But there's an easy way to get rid of it. I'm going to divide this side by 3,000. Well, if I divide this side by 3,000, I got to divide that side by 3,000. Which should give me 16, right? 16. Okay, I need to pause for a second here. This 3,000 times 2 to the 3 over x really means 3,000 times by 2 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 indefinitely. We don't know how many times to stop. Can I combine this 3,000 by that 2? The answer is no. This 2 is being repeated indefinitely. We don't know how many times it's being repeated. The 3,000, though, is literally being written there one time. So since there's only one 3,000, I can divide that 3,000 away from both sides if I want. Does that make sense? But I cannot combine the 3,000 with the 2. Because if you did that, then it would give you 6,000. And then it would be 6,000 times 6,000 times 6,000. And that's not the same thing as 3,000 being doubled over and over again. So, anyways, now this is actually pretty easy to solve. 16 is 2 to the 4. This is 2 to the 3 over x. Cancel the 2's. 4 equals 3 over x. So x equals 3 over 4. Let me know if I lost you on the algebra parts of that. What does that mean? Well, it means it takes 3/4 of an hour for bacteria to double. Every 45 minutes, your bacteria have doubled. Watch this. I'm going to grab a calculator just to confirm this. I'm going to take 3,000 and I'm going to double it once. That would have been 45 minutes. Then I'm going to double it again. Another 45 minutes would make it an hour and a half. Then I'm going to double it again. Another 45 minutes would make it 2¼ hours. And then I'm going to double it one more time. 2¼ plus 45 more would give you 3 hours. After 3 hours, we're up to 48,000. That makes sense? The hardest part, bar none, for kids, that stupid exponent. It's always a fraction, and you have to figure out whether the x is on the top or on the bottom. So I write this on the bottom of some of my slides here. I was talking with the other Math 31 girl briefly. Did she talk about this little thing down here a whole ton? You guys feel comfortable with the difference between the two? Okay, we'll move on then. Okay, let's try another one. Okay, word problem. You've got a thyroid deficiency. I don't even think it matters what that is, but they throw in a radioactive iodide with a half-life of 8.2 days. This little piece of information here gave you a ton. Do you guys talk about this in bio? Sweet. Okay, so overlap. What does a half-life imply? A half-life is when there's half of what there once was, right? So that half-life, that's your base. You're going to be timesing by a half over and over and over again. You started with 100, then you're down to half, 50, down to half, 25, down to half, 12 and a half, right? Tells you there's a half-life of 8.2 days. That 8.2 is one of these two numbers in the fraction. Oh, this is where it's hard. Is it the top one or the bottom one? It's the bottom one. Okay. The reason why it's the bottom one is the top number is the time that has actually elapsed, and the bottom number is the period, the time that it takes to get cut in half or tripled or something like that. So we know that every 8.2 days, it gets cut in half. Here's how I like to visualize it if I'm really struggling. I put the number on the bottom first, and then I try to make sense of it. And I say, okay, if it had been 8.2 days, 8.2 would divide by 8.2, giving me 1, which means that I would cut this in half once. That seems to fit, right? If it's been 8.2 days, it gets cut in half once. If I'm not sure how long it takes to get cut in half or double or triple, which is the last question, and then I put the variable on the bottom. So I'm going to put x up top and 8.2 down here. Okay, then it says how long should only 25% of the iodine be present? It doesn't seem like that's a lot of information, but 25% actually is. 25% is 25 out of 100. That actually tells you two things. It means that you started at 100, and eventually you want to end at 25. See how that's really subtle? 25% actually tells you two numbers, 25 and 100. The 100 is what you would have started with, right? You started at a full 100% capacity, and eventually you're down to 25%. Is able to get the equation? Again, I feel like this is the hardest thing to do. Write the equation. At this point here, you have three options. Option 1, type it in your graphing calculator. Most kids got that one down. Option 2, when we teach you it, use logarithms. You don't know that one yet, so let's do option 3. Let's try using common bases. It doesn't look like I can use common bases, but this leading coefficient of 100 right here, I can divide both sides by it. What's 25 over 100? Well, it's 25%, but as a fraction, 1/4. Am I still good? 1/4. Come on. 1/4. 2 to the minus 2. There you go. 1/2. 2 to the... Nice, good job. Yeah. Okay, that minus 1 still has to get multiplied by the x over 8.2, though. Don't forget, it still has to multiply into that remaining piece there. But hopefully you can kind of visualize. Those 2's are going to cancel. You are left with -2 equaling -1 times x over 8.2. To get an x by itself is pretty easy. Times the 8.2 to the other side, and then divide by -1. So -2 times by 8.2 would be -16.4. That'd be equal to -1x. So divide by -1. Actually, that makes a lot of sense, though. There's the negatives, right? Because if x was negative, that might not make a lot of sense that it's negative time, but negative divide by negative. X is 16.4. What is it, like days? Days. Think this through. On day 1, when you start, let's call it day 0, actually. Day 0. On day 0, when you start, you have 100%. 8.2 days later, half of 100 would be 50, right? 8.2 more days later means our running total is now up to 16.4. What's half of 50? It makes sense, right? Everything seems to fit. So the point I have, like the reason why I put these 2 slides back to back, is to try to help you figure out that stupid exponent. Because usually x is either the top or bottom of the exponent. You got to figure out which one goes where. You follow? Okay, last one. Now let's put it together with what we just learned with our graphing calculator. So I've got a scenario here where you've got tigers on a reserve in India. I mean, really, the context of the word problem is really irrelevant. Hopefully you can kind of see that it sure looks like the population growth seems to be increasing. I want you guys to figure out when it reaches 5,600. Okay. Well, if you have enough information, you could try to write yourself your own equation. But if you don't have enough information, a fourth option is to use your calculator in that whole list sort of concept. So there is actually one last default option that you could use. You can delete all of the data that's previously in there, and you can use your calculator to make yourself an equation for you. You know what I'm saying here? So if you are really struggling, now I hesitate to tell kids to go to this method first, because this one takes a while, right? Like this is a lot of button pushing. But I mean, if I give you data, you should be able to take this data, type it in. Okay, just don't type it in wrong. That's the worst mistake. 1097, 1156, 1362, 1789, 2627. Oh, were you asking how to clear? The fastest way of clearing, rather than just pressing delete one at a time, go up to L2 and press clear. Like go up physically to where it says L2, press the clear button. Give you a second to kind of catch up here for typing in that data. It doesn't appear to be linear growth, right? Because linear would mean it's going up by the same number every time, right? And it's going from like just under 11,000 to just under 1,100 to just over 1,100. But like then the next year it goes up by about 200, and the year after that it goes up by about 400, and then after that it goes up by like 800. Right? So like it looks like the amount it's going up by is not consistent every time, right? So if you can type this data in and go stat calculate an exponential regression, depending on your calculator type, you got to do the whole L1, L2. You don't need to care which Y you pick, just pick one of them. Like, I don't know, just pick Y1, who cares? If you were to then press enter, it now will give you a line of best fit. A should be your leading coefficient. Based on this data here, what should have our like leading coefficient probably have been? Your leading coefficient is what happens when there's like no time on the clock before you start, like when you start. It probably should have been 1097. It was actually 982. Okay, it's off by a little bit. That being said, do recognize this is not a connect the dots sort of scenario. It's a try to do it as best you can. Right? And your calculator finds the most efficient way of doing it. So it's pretty close. Does it go up by, well, what percentage does it go up by every year? Not 1.15%. It goes up by 11.5%. You catch that? Okay. Here's another thought. Go to your table of values and just make sure that the table is roughly what you're expecting. So 0's at 1082. Okay, it's a little low. 2 is now at 1222. That's a little bit on the high side, but it's pretty close. 4 is at 1362. Okay, it's out a little ways, but it's kind of close. It's mirroring it. 6 is at 1891. Yeah, that's roughly in the ballpark there. I know they're not fantastic, but they're roughly in the ballpark, right? 8. Look, now 8 is at 2227. It looks like there's a bit of an anomaly. This point might have been a little bit too high for what it should have been. But this is more or less like if we were to have plotted them, this is what they would have looked like. The graph is more or less going through like most of the points. It's not perfect, but like it's pretty close. Okay, the point I want to make on this one here is, are we going to be able to solve this equation right here with like bases? There's no way 982.3 I'm going to get like bases. So we really have no choice. We're going to have to put another line on here at 5600 and just see where they cross, which is fine. That's a totally valid way of doing things if you have that information. So I kind of like to finish with that one just to remind you that if you want to, use your graphing calculator. Find where two things cross. Right? I think the best slide to focus on for a summary would be this one back here. Okay. I need you to be able to solve exponential functions. It's very hard to solve for exponents because of the fact that they're hiding up there as an exponent. So option 1, use your graphing calculator. Just find where they cross. Option 2, if you have the right parameters, use like bases. Option 3, which we'll learn about next week, Monday, or whenever we get to it, we'll learn about how you can use logarithms to help you solve these as well. Make sense? Okay, summary of what we've learned so far in this unit then. There's 4 functions I have to teach you about. The 4 functions are your square root function, your fractional functions, your exponential functions, and your logarithm functions. We've covered 3 out of the 4. In each of those sections, you need to be able to know the subtle nuances of what involves those functions. Like, for example, you can't square root a negative, right? You need to know what the graphs look like, and you need to be able to solve them. In order to move forward, though, we still want to continue working with exponential functions, but one of the ways that we can solve exponential functions is using logarithms. So one of the next things we have to do then is start talking about what logarithms are. So the way the course is going to end is we're going to spend a couple of days talking about logarithms, and then we're going to loop back to this concept and learn again about how to solve exponent stuff, but using what we've learned about logs. So just so you guys are aware, we're basically 3/4 of the way down this unit. Okay, in terms of curriculum-wise. So what I need for you guys to do is with like 5 minutes today, so not that much time today, mostly tomorrow, start on the assignment now, okay? And get used to that. And then the plan will be work on the assignment tomorrow plus through the weekend or whatever. Monday we'll start with like some of the logarithm stuff. Tuesday's a work day, and Wednesday we're going to try another quiz. Okay. Sound good? Do you guys have any questions for me? It made at least sense where you're like, I can follow this? Did I kind of solidify it from yesterday? Okay, cool. Okay, you have like 8 minutes left, so, I mean, whatever. I guess pull out your assignment and see it. Do you have your assignments printed off yet? Oh, okay. Maybe do that before you go then. Print the assignment then.